This is lecture video 52, and we will cover improper integrals in this lecture. So up to now, we have required definite integrals to have two properties. First, that the domain of the integration, the interval a to b, is finite. Second, that the range of the integrand function is finite on this interval of integration. So this means that, in other words, f of x should be continuous on a to b. So if these two conditions are satisfied, the integral from a to b f of x dx is a very nice definite integral, and you can use integration rules to find the result to integrate it. But in practice, we may have some problems about these two conditions. For example, the area under the curve y equals e to the power minus x over 2 from 0 to infinite, the integral corresponding to this area is an example for which the interval of integration is not finite. So this first condition is not satisfied here because the interval of integration, which is 0 to infinite, is not finite. It is an infinite interval. Okay, the problem is this one in this first case. And the area under the curve y equals 1 over x is computed by this integral, from 0 to 1. If you consider this area, it corresponds to this integral, and this is an example of the case where the range of the integrand function is not finite. So range of f of x is not finite, let's say. It is infinite. In other words, f of x has a discontinuity point, is discontinuous at x equals 0, where 0 is one of the endpoints of your interval. So that's why the second condition is not satisfied in the second example. So these two examples, the integrals in these two examples, cannot be treated as the normal definite integrals because there are problems about these two conditions. So we will treat such integrals that has either the interval of integration is infinite, or that has a function having a discontinuity point at one of the over the interval of integration. We will treat those kind of intervals differently than the definite integrals. Either case, the integral is said to be improper, and they will be calculated as limits. So we will be treating them differently than the definite integrals. So after introducing improper integrals, the idea behind that, now we can consider in details type 1 integrals and type 2 improper integrals. Type 1 corresponds to the case that the interval of integration is infinite. Type 2 corresponds to the case that your function has discontinuity points over the interval of integration. Okay, so let's investigate type 1 first. Improper integrals of type 1. In this case, as we said, your interval of integration is infinite. I'm sorry. You see, interval of integration is infinite. This is the problem. That's why we are calling them as improper. They are not usual definite integrals for us. So it can be of this form, from a finite real number a to infinity. So how do we handle the problem here? The problem is the interval being infinite, right? That's why we try to fix this problem by putting a finite variable, for example, b here for the problematic part. And then how to transform the right-hand side to exactly what we have on the left-hand side is this way. You can just send b to infinity to have an exact equality between left and right. And look at the second case, please. Still, the interval of the integration is infinite, and we want to fix the problem by naming that minus infinity part as a variable. And then if you send a to minus infinity, you will be safe that the right-hand side and the left-hand side will be the same. Okay, in the third case, you see we have both minus infinity and plus infinity at the lower and upper bounds. So we need to fix them both, right? That's why, first of all, you can consider to divide the integral into two parts at a middle point like C. Okay, so you start from minus infinity, go up to C, and then you start C and keep going up to plus infinity. Then you understand that this first term looks exactly like the second case here, right? This is the second case that we have covered above. By the way, here C is a real number, and this looks exactly like the case in the first item. So this is the first case. That's why we know how to handle them. In the first case, for the first term here, you can just put some variable for the minus infinity part as we did in the second case. So let's put a here. C is still a number there, f of x dx, and then all I need to do is to send this number a to minus infinity, plus, and then I can fix the problem at this plus infinity here by naming that part as a variable, like let's call it as b, okay? And then if I send b to infinity, then everything will be the same on the left and on the right. Okay, so this b is written for this plus infinite, then I send b to infinity. This a is written for the minus infinity here, then I send a to minus infinity. So that's how you fix the problem of having infinite interval of integral by using limits like this. This is called the improper integral of type 1. Okay, so let's move on. This is the first example. And as you noticed, this minus infinity at the lower bound of the integral makes it as an improper integral. So interval of integration is infinite. That's why this is an improper integral of type 1. So we need to use limits to fix the problem. That's why now I will write, okay, for minus infinity part, I will put a variable, then the rest is as it is, to the x squared plus 4, and then I need to put this limit as a goes to minus infinity, because here we have minus infinity. Okay, after handling the integrating, I will compute an extra limit to find the result of the improper integral. So let's recall some integration rules here. You remember that 1 plus x squared, integral of 1 over 1 plus x squared is arctangent x plus c. Let's consider the more general version of this form, like instead of 1, I want to put a square here. Then the result is, the rule is, you put, okay, it starts then by 1 over a, and then arctangent x over a. Okay, this is the result if you have a square instead of just 1 here. So look at our structure, it is exactly like that. That's why I will integrate it as, okay, these two can go out, right? Okay, it is these two that I put out. It is 1 over a. What is a here? So a square is 4, a is 2. So I am using this property. It is 1 over a arctangent x over a, like that. And we have boundaries, you see. Then I will evaluate from a to 2 of this expression. And at the most outer part, I will compute a limit as a goes to minus infinity. Okay, so what do we have here on the right-hand side? Let's put the limit again. Okay, so limit a goes to minus infinity. What do I have here? I'm sorry. These are simplified. Maybe. Okay, these two are gone. Like that. So insert now x equals 2. It means that arctangent 1. Then insert a. Arctangent a. Okay. So what is arctangent 1? It is 45 degrees, so pi over 4. So the result is, what is arctangent a? As a goes to minus infinity, you need to remember now the graph of the arctangent function. Okay, it lies between minus pi over 2 and plus pi over 2, if you remember. Okay, its graph is like that, where this is pi over 2 and this point is minus pi over 2. Then you can tell me the limit of this function as a goes to minus infinity. So the result is minus pi over 2 for this part. That's why the result of the improper integral is plus pi over 4 minus pi over 2. So the result is a finite number, you see? It's a finite number. Even if the interval of the integration is infinite, here, this is an improper integral because the interval of integration is infinite. Even if the interval of integration is infinite, the result may be finite. Then you will call your improper integral as a convergent one. Okay, if the result is finite, you call your improper integral as a convergent. Improper integral converges, or you can say that it is convergent if the result is finite. Okay. So let's move on with the second example. This time we want to integrate 1 over 1 plus x squared over this interval from minus infinity to plus infinity. Again, this is an improper integral of type 1 because the interval of integration is infinite. So infinite interval, meaning that this is an improper integral of type 1. How do we handle it? This fits to the third case here, right? We will divide it into two parts. And you can use c equals 0 here to make your computations more simpler. Okay, the x over 1 plus x squared, then you continue from 0 to plus infinity. And you know how to handle this type of improper integrals. You name the lower boundary as some number, and then you need to send that variable as some variable and send it to the actual place like minus infinity. Okay, then the second one. This is the problem, so name it as b. 1 plus x squared, 0. And then you need to send this b to where it belongs, to plus infinity. Okay, after handling the integrations, we need to take limits. So let's keep computing. Limit as a goes to infinity. What is the result of this integral? It is, of course, arctangent x from a to, this is 0, remember, a to 0, and similarly the other term, b goes to infinity. Okay, we have again arctangent x. From where to where? From 0 to b this time. Okay, so what do we have inside the limit? Limit as a goes to infinity, arctangent 0 minus arctangent a. This is our first limit. We have also the second term. A goes to minus infinity. Okay, plus again, limit b goes to plus infinity this time, of what? Of arctangent b minus arctangent 0. Okay. So, like this one, arctangent 0 is 0, and arctangent minus infinite is minus pi over 2. And arctangent plus infinite is here, right? It is plus pi over 2. So the result for this improper integral is minus minus plus, and we have another plus pi over 2 here, so the result is pi. So this integral from minus infinity to infinity of this function corresponds to area under that curve over the whole real number from minus infinity to plus infinity. We computed this integral by treating it as an improper integral of type 1, like by also using the limits, we computed the result as pi. So the result of the improper integral is finite, then you can call this improper integral as convergent. This converges because the result is finite. Okay, and finally in this lecture video, I will talk about this famous this famous integral that we will be making use of it to solve the questions in the next section. So this is an improper integral of type 1 again, because the interval is infinite, of type 1. And we will try to find the result depending on p for this improper integral, okay? So let me remove this solution and let's try to handle it together. So first of all, we want to assume that the number p is different than 1. By the way, here p is a real number which is greater than 0, okay? So why I need to exclude first where p equals 1? Because if you have p equals 1, you obtain this type of integral, which is evaluated as ln, right? If you have some different number p, like 3, for example, it is evaluated by adding 1 to the power, dividing by the same power. So it is a power function, so minus 2 over minus 2. That's why we need to exclude where p, okay, this is the case where p, this is the case where p is different than 1. You always obtain a power function. So p equals 1 and p different than 1 should be treated differently because the integration rules are different. That's why we start by covering the case where p is different than 1. Then we will also cover the case where p equals 1. Okay, so what we have? We have the integral from 1 to infinity dx over x to the power p. Now we can try to fix the improper integral of type 1 by putting some variable here like b, okay? And then we can send p to infinity. And inside the integral, we have a power function like this. Okay, so what we have limit b goes to infinity. This is from 1 to b x to the power minus p dx. We know how to integrate such power functions. We add 1 to the power and then we divide by the same power. P goes to infinity. I add 1 to the power, I divide by the same power. Then it is time to insert upper-lower boundaries. Then I will take the limit. Okay, so we are inserting these boundaries for x, like that. Okay, what we have? Limit b goes to infinity, insert b first. Okay, I insert b to the power 1 minus b divided by 1 minus b, and then I insert 1. 1 to the power 1 minus b divided by this same same denominator. That's why let's take it out as a common factor, 1 minus p, okay? So this is what we have. And then you have take this constant out from the limit because it does not depend on b, right? So 1 over 1 minus p, limit b goes to infinity. We will deal with this limit now, minus 1. Okay, so at this point, we need to think smart. If, if 1 minus p is, okay, let's consider it like that. If this power is positive, so if p is less than 1, then 1 minus p will be greater than 0, right? Then b to the power 1 minus p is what as b goes to infinity. So you have a positive power and you send the base to infinity. So the result will be infinite, of course. So in this case, what we have as the overall result? So infinite over 1 minus p. So the result will be infinite. Now let's consider the other case where b is greater than 1. Then 1 minus p is less than 0. And then b to the power 1 minus p as b goes to infinity is what? So you have a negative power this time. Okay, this is negative, the power is negative here. So it is kind of infinity, sorry, some number, okay, it is kind of, you are sending b to infinity, so kind of infinity to the negative power, right? So this will go to, this will be kind of 1 over infinite, so 0. That's why in this case, this limit will be 0, okay? And here what we had, the power was positive and you are sending b to infinity. So in that case, we were having infinity to the power something positive. So it is directly infinite, right? Or if you need more explanations, okay, I can give you very quick examples. Example, limit x to the power 5 as x goes to infinite is infinite, right? As we have here, some power positive. And in the second case, we have a negative power, x to the power minus 5, and we send x to infinity. Then this is like that, 1 over infinite, 0. That's why we obtain 0 here. So the overall result in this case is infinite, where the final result, 1 over 1 minus p times infinite is infinite, and here 1 over 1 minus p times, okay, this part goes to 0 this case, so minus 1 times this. So the result is 1 over p minus 1 in that case. Okay, I am talking about this overall limit at the end. Okay, these are the results for the whole limit in these two different cases. Okay, then what we obtain, it can be written like that. We were searching for the result of this integral, which is an improper integral of type 1. So depending on the values of p, we obtain different results, right? What we obtain, if p is greater than 1, we obtain that the result is finite, right? So the result is like that. So let's call it as, since the result is a finite number here, you can call this improper integral as convergent, and it converges to this finite value where p is greater than 1. What if p is less than 1? Then we obtain infinite as a result. Sorry, I wrote it 0, but it should be infinite, okay? So then the result is infinite. That's why this improper integral is divergent. It diverges to infinity. The only remaining excluded case is when p equals 1. You see, we excluded at the beginning. So let's also cover that case here. What if p equals 1? Then your improper integral looks like this, and you can easily handle it by putting b here. Limit p goes to infinity, 1 over x dx. This will be evaluated as the ln function, ln absolute sine of x, from x equals 1 to x equals b. So what we have, limit b goes to infinity, ln b minus ln 1. So ln 1 is 0. If b goes to infinity, ln infinite is infinite. That's why the result is infinite if p equals 1. So the improper integral diverges in this case. This is divergent, diverges to infinity. That's why I will include p equals 1 case to the divergent part like that. So the integral from 1 to infinity dx over x to the power p, the result changes depending on the value of p. If p is greater than 1, it is convergent. If p is less than or equal to 1, it is a divergent improper integral. And I stop here. Thank you for your attention.